There is a number that changes the question. Not the answer. Not yet. The question. The number is 3.5 billion. That is how many years the organic molecules found inside Mary Anning 3, a piece of Martian rock drilled by the Curiosity rover in a clay deposit at the bottom of an ancient lake, have been sitting there, in the dark, in the rock, preserved through the collapse of a planetary magnetic field, preserved through the loss of an entire atmosphere, preserved through 3.5 billion years of radiation bombardment that should, by every reasonable expectation, have destroyed them. They were not destroyed. Among them, a nitrogen heterocycle, a ring of carbon atoms in which one position is occupied by nitrogen instead of carbon, a molecular shape that, on Earth, is the structural template from which nucleobases are built, the 4 chemical letters of the DNA alphabet. Not DNA itself, not a gene, not a cell, not a metabolic cycle. A precursor, the kind of molecule that, under the right conditions, with the right chemistry, with enough time, becomes the molecule that life uses to copy itself. It had never been found on Mars before. Not on the surface. Not in any Martian meteorite studied on Earth. Not in any previous experiment Curiosity or any other rover had run. The paper's lead author, Amy Williams of the University of Florida, said it plainly. Nitrogen heterocycles have never been found before on the Martian surface or confirmed in Martian meteorites. The Aegis has been calibrated for this mission differently from any previous assignment. Not for heat. Ancient Mars is cold, Iceland cold, not Venus cold, not Big Bang cold. Not for pressure. The ancient Martian atmosphere was thicker than today's, thin enough to require supplemental oxygen, but not dangerous by itself. Not for vacuum. Not for magnetic fields 10 orders of magnitude beyond anything biology can tolerate. The calibration for this mission is for age. 3.5 billion years is longer than the oldest multicellular life on Earth. It is 2/3 the age of the solar system. It is a duration so large that the human mind does not actually process it. It stores the number and moves on, the way a calculator displays a result it cannot draw. The suit will go to the bottom of an ancient lake on Mars, 3.5 billion years ago, to stand in the place where these molecules were first deposited in the mud, and ask the question that 20 organic compounds, including one nitrogen-bearing ring structure, have just made impossible to ignore. Was something alive here? Could you have survived it? You need to understand what has been lost before you can understand what was found. Mars now is the second driest surface in the solar system. Average temperature, -60 degrees Celsius. Atmospheric pressure, less than 1% of Earth's. Lower than the threshold at which water can remain liquid on a surface. No magnetic field of significance. A radiation environment so intense that the top few meters of Martian soil are continuously sterilized by cosmic rays, with organic molecules at the surface surviving for perhaps thousands of years before being destroyed. Nothing large lives there. Nothing small has been found to live there. The surface of Mars today is as close to chemically dead as a rocky world can be. But the rock the suit is standing in the Knockfarrell Hill member of Glen Torridon in Gale Crater, is 3.5 billion years old. And 3.5 billion years ago, this was not that Mars. This was a lake, not a brief, catastrophic flood, not a temporary accumulation of meltwater from a passing impact event. A persistent, stable lake, fed by rivers and streams flowing down from the surrounding highlands, with a chemistry that researchers have been able to reconstruct from the mineral record preserved in the rocks. The lake had a pH close to neutral. It had dissolved minerals, sodium, potassium, magnesium, calcium, sulfate, bicarbonate. It had iron in multiple oxidation states, creating the kind of redox gradient that chemists recognize as a potential energy source for microbial metabolism. It had, above it, a sky. The sky above Gale Lake 3.5 billion years ago was not the sky above Mars today. It was a real atmosphere, thicker than today's, capable of sustaining liquid water at the surface, capable of attenuating at least some of the radiation from the young sun. The best current estimates put the ancient Martian atmospheric pressure at somewhere between 0.5 and 1 bar, thin by Earth standards, but real, capable of weather, capable of rain. The closest thing on Earth to what ancient Gale Crater looked like. Iceland. Not the warm Mediterranean, not a tropical lagoon. Researchers compared Martian mudstone from Gale Crater with Earth's volcanic terrains and Iceland's cold, wet environment. Basaltic rock, glacial meltwater, temperatures typically below 4 degrees Celsius was the closest match. Cold, wet, geologically active. The kind of place on Earth where life appears in hot springs, in volcanic vents, under ice, in rock. The Gale Lake environment met the scientific definition of habitable for approximately 700 million years. Not a window, not an episode. 700 million years of conditions that would allow microbial life to exist if it were present. Longer than the entire span of complex animal evolution on Earth, from the first fish to the present day. The suit stands at the shore of that lake. The water is there. The chemistry is there. The minerals are there. The atmosphere is there. Thin but present. The sky that butterscotch orange that the Viking landers photographed in 1976, but with more substance behind it, more pressure, more protection. The young sun overhead, slightly dimmer in total luminosity than the sun today, but more active in ultraviolet, the radiation spectrum that damages organic chemistry. The suit's instruments are reading everything. The mud at the lake bottom, fine-grained clay minerals, smectite primarily, a clay that forms in liquid water and is known on Earth for one specific property that has nothing to do with its chemistry. Clay is exceptionally good at preserving organic molecules. The layered structure of clay minerals traps organic compounds between mineral sheets, physically shielding them from the reactions and radiation that would otherwise degrade them. On Earth, the oldest preserved organic molecules in the fossil record, organic remnants of ancient life surviving billions of years of geological change, are found in clay. The same mineral that records the ancient chemistry of Earth's oceans is recording the chemistry of this Martian lake right now, in the mud directly below the suit's feet. Whatever is in this mud will still be there in 3.5 billion years. The question is, what is in the mud? The answer required an experiment that had never been performed on another world. Curiosity's main chemistry instrument, SAM, the Sample Analysis at Mars Suite, has been finding organic molecules on Mars for years. Simple ones: methane, thiophenes, benzene, the kind of molecules that heat-based analysis can liberate from rock samples. Small, volatile, interpretable. These detections were scientifically significant. They were not sufficient. The problem with heat is that it destroys exactly what biologists most want to find. Heating a rock sample liberates small molecules, fragments, but breaks apart the larger organic structures that would carry the most biological information. A nucleobase heated to 800 degrees Celsius does not arrive at the detector as a nucleobase. It arrives as its components. The structural information, the specific ring geometry, the position of the nitrogen, the shape that makes a molecule biologically recognizable, is destroyed by the process of detection. TMAH, tetramethylammonium hydroxide, works differently. It is a wet chemistry reagent that breaks large organic molecules at specific chemical bonds, releasing their structural components without heating them to destruction. The experiment dissolves the rock sample in the TMAH solution, and the resulting molecules are separated by gas chromatography and identified by mass spectrometry. Each molecule identified by its mass and fragmentation pattern, a chemical fingerprint. Curiosity carried exactly 2 cups of TMAH. 2. Not 200, not 20. 2 uses of this experiment for the entire mission. A mission that has been operating for 14 years and has driven over 35 kilometers across the Martian surface. 2 chances to run the most chemically sensitive organic detection experiment ever deployed on another planet. The team chose Mary Anning 3, the clay-bearing sandstone at the base of Glen Torridon, because clay preserves organics, because the location was ancient enough to be geologically relevant, and because the ancient lake environment was the most compelling target available. The experiment worked. The results showed the in situ detection of more than 20 organic molecules from clay-bearing sandstones in the approximately 3.5 billion-year-old Knockfarrell Hill member of Glen Torridon. Benzothiophene, methylbenzoate, single and dicyclic aromatic compounds, a suite of complex carbon-containing molecules, diverse and structured, not the simple fragments that previous experiments had found. And among them, the nitrogen heterocycle, the ring structure with nitrogen, the molecular shape that, in Earth's biochemistry, is the template for the letters of the genetic code. These findings are important because they confirm that larger, complex organic matter is preserved on Mars over geologic time periods, despite the harsh radiation environment, Williams said. This is the sentence that changes the calculation. Not that life existed, not that the molecules are biological, that complex organic matter, large, structured, chemically informative, can survive on Mars for 3.5 billion years. This matters because it means that if life ever existed on Mars, its chemical trace is recoverable. The evidence has not been erased. The 3.5 billion year clock has not destroyed what was there. The question that Mary Anning 3 answers is not, was there life on Mars? The question it answers is, if there was life on Mars, could we still find its chemistry? The answer is yes. Which means the next question is now genuinely worth asking. 20+ organic molecules. One nitrogen-bearing ring structure never before detected on Mars. Preserved intact for 3.5 billion years in clay at the bottom of an ancient lake. Where did they come from? 3 possibilities. The science cannot yet distinguish between them. The first, they fell from the sky. Mars, like Earth, like every rocky body in the inner solar system, was bombarded by meteorites throughout its early history. Carbonaceous chondrites, the most chemically primitive type of meteorite, contain abundant organic chemistry, including amino acids, nucleobases, and aromatic compounds that formed in the interstellar medium long before the solar system existed. These molecules are ancient, older than the Sun, assembled in the molecular clouds between stars by ultraviolet radiation acting on simple ices. They arrive pre-made, pre-assembled, the prebiotic chemistry of the galaxy, distributed uniformly to every world that orbits a star. The same stuff that rained down on Mars from meteorites is what rained down on Earth, Williams noted, and it probably provided the building blocks for life as we know it on our planet. The nitrogen heterocycle in Mary Anning 3 could be this: a fragment of meteoritic organic chemistry delivered from space, preserved in clay, not Martian in origin, cosmic. The second, they were made in the rock. Certain geological reactions produce organic molecules without biology. Serpentinization, water reacting with iron and magnesium-rich rocks, generates hydrogen, which can drive the abiotic synthesis of organic compounds. Hydrothermal chemistry produces aromatic structures. Fischer-Tropsch synthesis, occurring in volcanic systems, generates aliphatic carbon chains. Ancient Mars, geologically active, volcanically alive, saturated with liquid water in some regions, was running all of these reactions simultaneously. The organic molecules in Mary Anning 3 could be this: the products of water-rock chemistry in an active geological system. Not biological, not cosmic, local. Martian geology making Martian chemistry, the same way Earth's geology makes organic molecules in hydrothermal vents today, in environments that, on Earth, also happen to support life. The third, they are what remains of something that lived. The organic molecules in Mary Anning 3 could be the degraded remnants of Martian biology, the chemical trace of organisms that used these molecules not as geological byproducts, but as functional biochemistry. The nitrogen heterocycle, not a precursor to nucleobases, but a fragment of them. The benzothiophene, not a meteoritic aromatic, but a decomposition product of sulfur-containing biological molecules. 3.5 billion years of radiation and geological change, breaking down what was once organized, functional, alive, into fragments that the TMAH experiment can still identify by shape because clay preserved the shapes. Without in-person examinations on the red planet, it remains unclear if these compounds came from past life forms, from a meteorite crashing into the planet, or through geological processes. The paper does not choose. The science cannot yet choose. What it establishes, what is beyond scientific doubt, is that the molecules are there, that they are complex, that they include a structure never before seen on Mars, and that they survived. In all three cases, the same conclusion follows. The prebiotic chemistry of life was present on Mars. Whether it remained prebiotic or became something more is the question that Mary Anning 3 has just opened. The suit's biological monitoring systems are running continuous analysis of the environment. Temperature, cold. Iceland cold. The shoreline of Gale Lake, 3.5 billion years ago, sits at perhaps 0 to 4 degrees Celsius on a mild day, the same temperature range as the sedimentary lake environments in Iceland that researchers used as the closest analog. Not comfortable without thermal protection, not lethal. Cold in the way that demands preparation, not the way that kills in seconds. Pressure, manageable. The ancient Martian atmosphere, between 0.5 and 1 bar of pressure, is thinner than Earth's, but physically survivable with supplemental oxygen. The air is not breathable. Carbon dioxide, nitrogen, some argon, essentially no oxygen. But the pressure itself would not rupture a lung, would not cause the uncontrolled expansion of gas in tissue, would not kill the way that Mars today would kill the moment a suit was breached. Radiation, the real problem. Mars's magnetic field 3.5 billion years ago was already weakening. The planet's smaller size meant its iron core was cooling faster than Earth's, the convective motion that generates a planetary magnetic field slowing, the field becoming patchy and inconsistent. Not gone, not yet, but not the reliable global shield that Earth's field provides. The solar wind reached the upper Martian atmosphere and interacted with it, slowly stripping it away. The process that over the next billion years would reduce a thick, weather-bearing atmosphere to the thin ghost that exists today. At the surface, ultraviolet radiation from the young sun, more active in UV than the present sun, reaching the ground at levels substantially above what Earth's atmosphere and magnetic field reduce it to. The suit's UV sensors register a continuous, significant flux, not the lethal immediacy of a neutron star's radiation field, not the quantum critical regime of a Magnetar's magnetic environment. Slower, cumulative. The kind of radiation that does not kill you in a moment. It damages DNA in your cells, one photon at a time, and the damage accumulates. 10 minutes of exposure to midday UV at the Martian surface 3.5 billion years ago without UV protection. Measurable DNA damage in unprotected skin. Not death, a beginning. The kind of beginning that, compounded over days, becomes the kind of damage that becomes cancer. With UV-resistant suit material, survivable. With oxygen supply, thermal management, radiation monitoring, physically, for a limited time, this environment is within the envelope of human tolerance. The suit's instruments are finding something else. In the water at the lake's edge, in the mud at the shore, in the fine clay particles suspended in the shallows, the chemical sensors are registering the molecules that Mary Anning 3 preserved. Not as fossils, not as fragments in ancient rock. Fresh, dissolved, present. The nitrogen heterocycle in solution. The aromatic compounds in the water. The chemistry that will, eventually, 3.5 billion years from now, be locked in clay and drilled by a robot the size of a car and dissolved in one of 2 cups of a reagent that only works once. The suit's biological hazard assessment runs a calculation that has no reference entry in its mission library. Unknown biology, potentially active. Unknown pathogenicity. Unknown compatibility with human immune function. Unknown interaction with human biochemistry. HUD. Biological environment, uncharacterized. Organic chemistry, complex, nitrogen-bearing. Life probability, cannot assess, insufficient data. Recommendation, do not breach suit integrity. This is the survival problem that ancient Mars presents, and it is not the environment. Your immune system has evolved over millions of years in response to the biology of Earth. Every pathogen it knows it has met before, or it has met something enough like it that the recognition machinery can respond. The antibodies, the T cells, the inflammatory cascade, these are a library built from encounters. The biology of Mars, if it exists at all, has never met anything like you. Your immune system has never encountered anything like it. Whether Martian microbiology, if present, is pathogenic, is a question that cannot be answered without encountering it. It may be completely incompatible with human tissue. It may be entirely indifferent. It may be something for which neither word applies, because the biochemistry is different enough that pathogenic and harmless are categories that don't translate. The extremophiles in Earth's hydrothermal vents do not harm humans. The bacteria in Atacama salt crystals do not harm humans. The organisms that live in pH1 acid streams do not harm humans. But they evolved in the same biosphere. They share the same genetic code. They use the same 20 amino acids. The rules of their biology and the rules of your biology are written in the same alphabet. What is in Gale Lake, if anything is in Gale Lake, may not share a single letter. The suit holds. You would survive the temperature. You would survive the pressure. You would survive the radiation. For a time, with protection. What you would not survive, what no immune system built on Earth biology could survive unchanged, is becoming the first point of contact between two biospheres that have had 3.5 billion years to diverge. The lake surface catches the light of a slightly dimmer, slightly younger sun. The clay at the bottom is recording everything. The minerals are doing what clay minerals do, trapping organic molecules between their layers, preserving molecular geometry, protecting chemical structure from the reactions that would otherwise unmake it. The process is slow and not deliberate. Clay does not choose what to preserve. It preserves whatever settles into it. The molecules are settling now. The nitrogen heterocycle. In solution, then adsorbed onto a clay particle, then buried under another layer of sediment as the lake level rises and the mud accumulates. The benzothiophene, the same. The methylbenzoate, the same. Each molecule finding its way into the mineral record, shielded from what will come. What will come is catastrophic. Not immediately. Not in any time frame that anything living in this lake would experience as a threat. But the magnetic field is weakening. The solar wind is beginning its work on the upper atmosphere, one ion at a time. the slow stripping that will take hundreds of millions of years to complete. The sun is brightening with age. Its luminosity will increase over the next billion years, changing the thermal balance of a world already losing its protection.
The lakes will thin, the rivers will slow, the atmosphere will thin, and the UV that the thinning atmosphere no longer blocks will reach the surface in increasing intensity. Life, if it is there, will retreat deeper into rock, deeper into the subsurface, into the places where the radiation cannot reach and the last pockets of liquid water persist, warmed by residual geothermal heat in the dark for as long as the heat lasts. Then, nothing. On the surface, nothing. The chemistry locked in clay, waiting. 3.5 billion years later. A robot the size of a car, driven by a team of people 225 million kilometers away, drills a hole 5 centimeters deep in a rock at the exact location where the sediment accumulated, dissolves a fragment of that rock in one of its 2 available cups of a wet chemistry reagent, and identifies 20+ organic molecules, including 1 nitrogen-bearing ring structure never before detected on Mars. We think we're looking at organic matter that's been preserved on Mars for 3.5 billion years, said Amy Williams. It's really useful to have evidence that ancient organic matter is preserved, because that is a way to assess the habitability of an environment. And if we want to search for evidence of life in the form of preserved organic carbon, this demonstrates it's possible. The suit returns. The lake remains. For now, for the millions of years that remain of its life before the atmosphere fails. The clay continues its work. The molecules continue their preservation. What the suit carries back is not a sample. It is a question with a new shape. The Drake equation has a term for the fraction of habitable planets where life actually arises. It is called F sub L, and it is, in Frank Drake's original formulation, the most uncertain number in the equation. The number that determines whether the answer to "Are we alone?" is yes or no. If F sub L is near 0, life is a cosmic accident that happened once and will not happen again in any meaningful time frame. If F sub L is near 1, life is what chemistry does. Wherever you give it liquid water, organic molecules, and time. Earth cannot tell us which value is correct. Earth is a single data point. A sample size of 1 tells you nothing about probability. Mars is the second data point, not a confirmed second data point. Not yet. What the Marianning 3 experiment confirms is that the chemistry was present. Complex organics, including nitrogen-bearing structures that are chemical precursors to genetic molecules, preserved in an ancient lake environment that met the conditions for microbial life for 700 million years. If that chemistry became life, if F sub L is even small, and the 700 million year window on Mars was enough, then 2 consecutive habitable planets in the same solar system produced life. The nearest rocky neighbor, the planet next door. And if that is true, F sub L is not near 0. It is not a cosmic accident. It is chemistry doing what chemistry does when conditions permit. Every star with a habitable planet becomes a candidate. the number of inhabited worlds in the observable universe becomes not a philosophical abstraction, but an arithmetic result. And the arithmetic is large. Marianning 3 does not confirm this. A single rock, a single experiment, 20+ molecules. This is not proof of life. It is proof that the chemistry was there. It is proof that it survived. It is proof that the question is answerable. Future missions are being built to answer it. The Rosalind Franklin rover, named for the chemist whose X-ray crystallography revealed the double helix structure of DNA, is the European Space Agency's next Mars mission. Designed to drill deeper than Curiosity, reaching rock shielded from surface radiation by meters of overlying material, rock that has not seen the Martian sky since it was deposited. It carries an improved TMAH experiment, not 2 cups, more, with better instruments. With the explicit goal of finding what Marianning 3 suggested is waiting at depth. Dragonfly, which will arrive at Saturn's moon Titan in 2034, will carry similar wet chemistry to a world with lakes of liquid methane and a surface covered in prebiotic organic compounds, the same class of complex organic chemistry in a completely different solvent under a completely different sky. 2 missions, 2 worlds. The same question asked in 2 different chemical environments. The Aegis has been to environments where physics changes at the quantum level, where space-time is dragged by a spinning neutron star, where the plasma of the first second of the universe erased every distinction between matter and energy. None of those environments have produced a question as difficult as this one. Because those environments are hostile. They are extreme. They offer no ambiguity, no possibility of something living there, no possibility of a second origin of life, no possibility that the chemistry in the rock was once organized into a cell. This lake is different. This lake was the right temperature, the right chemistry, the right minerals, the right organic inventory, the right duration. Everything that life needs, present, stable, preserved. And the molecules to prove it, still sitting in the clay, 3.5 billion years later. The question is not whether Mars could have supported life. The evidence answers that. It could. The question is whether it did. And if it did, if something lived in this lake, metabolized the iron in the sediment, used the nitrogen heterocycle as a precursor to something more complex, copied itself in the quiet water before the sky began to change. What killed it? The answer to that question is not in Marianning 3. The answer is in the sky above the lake, in the solar wind that the weakening magnetic field could no longer deflect, in the atmosphere that the solar wind was slowly, inexorably stripping away, in the radiation that intensified as the protection thinned. The sun did not intend to kill Mars. The sun does not intend anything. It burns, and the wind it generates flows outward in every direction. And what that wind encounters depends on whether the planet it reaches has the protection to resist. Mars did not have enough. What the sun is capable of doing to an unprotected planet, how it strips atmospheres, erases the conditions for life, and turns a world that was once an Icelandic lake into a radiation-scoured desert is not a historical question about Mars.
It is a question about every planet that orbits a star, including this one. Could you have survived what was alive on Mars?
You would have survived the cold. You would have survived the thin air. You would have survived the radiation, for a time, with equipment. You would not have survived the encounter with the unknown, the chemistry of a biosphere that your immune system had no template for, that your biology had never prepared for, that your every defense was built against the wrong thing. But here is what you would have found, standing at the shore of Gale Lake, 3.5 billion years ago, in the cold, under a butterscotch sky, with your instruments reading nitrogen heterocycles dissolved in the water at your feet.
Evidence. Not proof. Evidence.
The most valuable thing in science. The thing that changes the question from, could there be life on Mars, to, why did it stop? The clay remembers. We just learned how to ask it. What should the Aegis face next? The answer to what killed Mars is not in the rock. It is in the sun. The same sun that drives the solar wind. The same sun that strips atmospheres. The same sun whose most violent events, the flares, the coronal mass ejections, the moments when it releases more energy in an hour than it produces in weeks, have been shaping and erasing planetary habitability since the solar system began. Subscribe to Could You? Because next, the Aegis goes to the source.